this morning I am going to show you some examples of several systems that I have already worked out the bone graft models, and so you can practice. And I have actually drawn the bone graft model over the system so that you can see the one-to-one correspondence. So let's take a look at this, and the idea here is that having these bone graft models, with any of this you can get state space form. So let's go one by one. So in here you have this you have the, hold on there, so I can see, yeah, there we go. Okay. You have two loops here. What I did is I put a one for this loop and another one for this loop, and as you know by the procedure now, we attach the elements that are attached to those ones. There you have the C element, on this one you have the I, on this you have the source. Now in between these two, the difference between these two is what the R sees, and this is the system that we a simple system that you find it in your textbook. However, I must warn you, as we were trying the other day, if you put an inductor in here instead of a resistor, then the derivation becomes difficult, because by the way you connect in here, you will have some algebraic loops, but that's not the issue that we want to discuss now. But let's move on with the see, this one is a little different because it has capacitor. So don't get me wrong, there's nothing wrong putting it in an inductor in the middle, but the problem is what happens if you have other things in there that will indicate. So in here we have let's see if I trying to get my a little circle in there, because it's good pointer. There we go. So in here, if we do the same thing, we put a one junction and we put a one junction for the other loop. You see we attach the C, the R element, we attach the C, the SC, and in between those two we have the I. Do you see? By now, once you get the practice with this, it becomes easier and easier. And in here, this is a system that has three equations, but it is something that you can very easily manage and quickly get your bone graft model. Let's take a look at another example in here. Here you have the circuit, which is more complex, and so in here you have this. Hold on for a second. We have now three loops. On these three loops, you have this one in here that represents the current on this loop, the other one that represents the current on the second loop, and the other one that corresponds the current on this loop. So in here you have a situation where we connect the one over here, you see, and then we connect this other one, the R element, and There we go. With a little hand is better. So we have in here the C element. You have the R element in here. On this one, you also the R. This the R. And now you go to the next step to do what's between them. The difference between this and this is done by the 0, is seen by this I. The difference between this and this is done by the 0 and seen by this I. So I went ahead and I put the the causal marks on this, and you will realize that this is also one of those examples, the way things are connected, that you will get an algebraic looping here. So it will be like the one I worked out last time, because you see the causal marks don't complete. That's why it's an indication that there is this kind of mathematical challenge. Now let's take a look now at this one. Okay, I began doing something to make things more efficient, and that is, you know what we have said in previous occasions, that we put this one junction to indicate the velocity 0. I think that's a very fine approach. There's nothing wrong with it. But you could begin simplifying things. Because it's 0, it's like this part of the bond graph doesn't exist. So you could simplify it by taking this branch and the other branch out. But I didn't want to do it at the beginning until you are very familiar with the technique. So what do we do here? One for each mass. So we put the I elements in there. And then we have one for, let's see, hold on. We put the I's in there. And then you have a, sorry guys, here this, yeah, there we go. So in between the wall and this, we have, of course, these two, and in here we have an AC, and then if we take this out, we will have an R element here. There's that R missing from this one here. When I worked out, I didn't write it in here, but I did in the bottom. So if you simplify, you see this R element gets to the one here, and the other one on this other side, the C also. So this would be the simplified bond graph model of this. The point being that you have to that you can simplify the ends. That's all I was trying to do here, just to make sure I don't mess up anybody here in the understanding. There is something in here that maybe we should complete correctly, so that nobody gets confused. And that is, see, let's try here. You see on this side, I need the red pen so that we do it right. Okay, right here we need this R element, see, this one. So you have this right here, this R element, and on the other side also I didn't write it, and I needed to. See here, you have these are over here. Then the bottom picture makes sense. Okay, the bottom picture makes sense. See here. Then you have that R element over here, and then you have, excuse me, it's not an R element, it's a C element that I need up there. You see this one right here. So I'm sorry. Please correct that. It's a C element, not an R element. Okay. So then let's go to this one over here. Of course, you can always redo this and make it a little more pretty, but I wanted you to see the wide application of all this. I don't know if you can see it clearly because of the lighting in here, but I think this would be much better for you to follow what I'm doing. See here, you have this you have the one junctions for each mass, those two ones. And in here you see there is a transformation between these gears. You notice that the way the problem is that the rotation of this mass is the rotation of this gear, but this one is a different angular velocity. So you have a one junction over here, and you're going to have another junction on this side. So that's why I put this one, and then I put, let's see, I put the other one also. So you have this hold on for a second. Yeah, so you have this one and this one, but you see in between this and this you have this C element. So let me back up a little bit. How do we start building this? 1, 1, 1. After we do the ones, we attach the elements. You have this R element, you have the I element, you have the TF in between these two, and you have this I. The only thing left to build is this one, and that's the angular velocity between this, and you get the 0. So I am building the systems right on the right over the physical system. This is one that you have also as an example in your textbook. And how do we actually build this? See, by now we need to get more and more advanced examples under our belt. And so in here we start by drawing the ones in here, the ones in here, the ones in here. Notice I suppress the ends. I am not ignoring them. It's just that by now I hope that you can see that if we set them to 0, we can reduce them, and that's why I have done this. So in here, what you have is you put the 1 here, the C and the R element in here. On this one, we need the I element. Where's the I element here? You see there's a little mistake in here. We need an I element right here, right there. And then we have the I over here too. Okay, so then we have this situation where the on this side we put the I, the C and the R element over here. Now let's try to understand this. When you have this, I believe in my my practice, you may say, putting a 1 in between these two makes it a lot easier to do the bond graph. because you can put the element this between two ones and this two, although they get reduced, but and then both of them hang off a zero, but for purposes of building the graph, it's actually at least easier to put it that way. So that's how to build this. So any of this would do for a state space form, and I wanted to touch bases on my comments that I did a moment ago about if you put inductor in this example in the middle is very different than if you put this resistor here. This example is pretty simple. This one is not. I think we'll see later on how to solve algebraic loops and derivative forms. But I just wanted to, I made some notes to myself, but I am sharing them with you such a way that you understand a little bit more the examples on your textbook in here. So this about the derivative causality is more on this, or algebraic loops is more towards that. But let's look at this example right here. All right. And what you have in here is that if we forget about the bond graph model for a moment, which by the way is simple in here, but let's just forget about this for a moment. There's another method to obtain the state space form, and that is take a look at every single I and every single C in the system and write the differential equation for that. But you see in here for this capacitor, that would be 1 over C the integral of I dt, right? The voltage for the inductor here would be L times d IL dt. But you see, we want the state space form once the equations in the form of first order derivatives, the state variables, and the inputs, nothing else. Okay, so how do we achieve this? Do you see this one over here? If instead of being in integral form, you put this equation in derivative form, do you see what you get? You get C times dBc dt equals to IE. Notice this. When you do this, this is what I was trying to think on how we explain this very easily, is this is the derivative right here, and so is this. So if in some way we find this variable b sub L and b sub IC in terms of the inputs and the state variables, we have achieved what we want. So like I say, I was writing it to myself, so I may have to basically read you again to make sure everybody understands what I wrote. It says if we find the right hand of these two, then we have it. We have the state space form. So what are state variables? They are the quantities that are differentiated, in this case b sub L and I sub C. Okay, so if this is true, here's the thing. You're used to writing the differential equations using Kirchhoff's laws, right? If you go this route, you will have to use a different substitution of variables to get it right. While if you keep at this 2, you see, we need to find out this current. So you see, it will say I sub C. Isn't it true that I sub C, this one, is I sub L minus isobar, right? That's what the equations at this node say. I don't know if maybe it might be a good idea for me to do a little drawing in here to make sure that we get this right. Say, I'll do that. Let's try this. In here, yeah, I think I'm gonna give it a try. Let's see here. This is what you have. This one in here, this is I sub L. This one in here, we call it I sub C, and this one we call it I sub R. So you see how it's written on the left hand side, and the left hand side is saying that I sub C, this one right here, this one is I sub L minus I sub R. That's what you have in here. Okay, it turns out if you do this, you see this one is already one of the state variables because you had it in here. See, you had it right there. I sub R. Now I'll go a little further up, right here. I sub C is this. So I sub L minus I sub R. So I sub L is the other state variable. So you have minus I sub R. So if you find I sub C, which is this one here, what has happened? If you substitute this, you get this equation. And this equation is in terms of just a first order derivative and the two state variables. See? And to do the other one, to do the second one, if you consider, when you do this kind of example, we consider this loop, or we can consider the loop outside. So if you do this, you know that the voltage on the inductor is equal to the or perhaps you can say that P this voltage is the inductor plus the capacitor voltage, or that the inductor is the B minus B sub C, which is what I have in here. See, and we want this because the other state variable is B sub L, is this one. So we only, and this is an input, so we only need to work on this. And if you do that, you see B sub C in here is 1 over, I mean, if you divide L, you have this in terms of B sub C and the inputs. And using these two equations, you can put them in a state space form. See? So this is another method. So either you do the computerized automated modeling method, or you do it this way. Or you can actually derive the three equations, and then, I mean, in second order form, 2 or 3, whatever number of loops you have, and then use the derivation. If there's no algebraic loops, they will be pretty straightforward. If not, they will be like the example I did last time. Hope this clarifies a little bit more. You have that in chapter 3 in your textbook, and see how to get the state space form. Now what we could do right now is we could take one of these examples, perhaps even this one, and let's take this example and put it into the CAMG software and see how you get state space form from this. Okay, so what I can do is just to make our life simpler, I am going to still just this picture so that we don't have any interference with anything else. That way we can have it next to our see here. There we go. Yeah, so what we can do is we can go to the CAMG software and put this in, but before that we do that, I would like to set up the output. You know, what is the output going to be for us? What is the output in here? Let's just do this in new one, and then we are going to do it like this. We'll move this down, and all I have is my bond graph model up there. How do we do this so that this is the least descriptive here? So I am looking at my picture in here, and at this point I need to define, this is an input, right, on the right hand, on this side over here on the left. That is an input here. See right here, this is the input. You have this this inertias in here, and what we would like to know is, for example, what is the torque on this mass in relationship to this input, or what is the the torque on this, or what is the force on this spring here, or the angular velocity with respect to this. So why don't we set this up so that we have as an objective what the outputs are. So in here, maybe what we could do is, let's just go ahead and number this 1 and 2, and then 3 and 4 and 5 and 6, 7, 8 and 9. Notice one thing is that we are we're not considering the mass of the pulleys of the gears, which we could. Okay, either we combine with the rotor, or we they become independent like the one on the bottom. But this is just for the sake of our example, and let's just define my output as in here my output is going to be let's just write it down here. So what is the velocity, and in this case the velocity, what did we say, the velocity or torque on this mass? We could do either way. Yeah, why don't we do the velocity? So f sub 8 in relationship to E1, this is one transfer function, and the other transfer function would be, let's say, the torque on the spring, which would be E sub 6 in relationship to E sub 1. Two transfer functions. Okay, so having done that, I go in here and I draw my bond graph model. Hopefully I can fit in here. Okay, and then we have this one in here, and this is from here to here, and then you have this I element over here, which is from here to here, and then we have the TF, which is from here to here, and then the way I did this, I put it down, you know, so this is the, you could do the one junction over here just to indicate those pulleys in there. And then what do we have going towards the left over here? Yeah, this idea that Windows makes it an entire screen, full screen, works against us here, but we'll try now. This is the 0 here, and we have in here from here to here, and then we have the C element over here from here to here, and then we go to the one with the I element over here from here to here, and then we have the I element over here from here to here, and then we have the R element that you have on the side that goes from here to here. This is the entire system as I have it on the left hand side, and you see my objective was F sub 8 and E sub 6, keep in mind. So now we are going to we'll leave the bond graph model up there, and let's move this a little bit here, and then let's just run this. And here you go to the MATLAB interface, and then we get this programs talking to each other, and then they would interact with each other. MATLAB will, so we have to be a little patient, and there it is, until CAMG and MATLAB work together, and it's all for a good cause, because we don't have to do all this derivation that you have seen in your textbook, and I also showed you a moment ago what you would have to do if you don't do this technology. So now once the program comes up, we will use the CAMG-SYM file in MATLAB, which CAMG send it to MATLAB from this bond graph model. So at this point we will have this let's see, we have to wait a little. This interface on this system takes its time, but there's nothing wrong with this. It's just coming up. The reason is that, you know, this is version 2015 of MATLAB, and it's coming through the network, and that slows it down, but it will come up. So we don't, we're just there we go. Okay, we're just waiting a little. And so remember F6 and E8, right? No, F8 and E6, that's what it was. And so what will happen now that MATLAB is up? There is this handshake between CAMG and MATLAB, and it will produce these M files that describe the system. So you'll see them in there. There they are. So this is the CAMG-SYM file. Let me perhaps do a bit of the preferences change here so you can see the 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 write up really well. So I'm just gonna put this in here and then make the font a little bigger. Yeah, there we go. So what you gotta do on this file, because we wanted in symbolic form, we need the to define the outputs, because the other matrices the system already knows. So in here we need to go to define, and then we say f sub 8 like this. Was it? Yeah, f sub 8, right? Okay. What is happening here is that in f sub 8 you go to the output equation of that f sub 8, and because CAMG doesn't know what you would like, you have to define it as the first output. But you see, when you are doing this, putting this 1, you are saying this is the first output, and this is part of my the first row of the C matrix. So, and in here we got, what was E sub 6, right? That was the second one, E sub 6, and then we did find it. Okay, you do the same procedure. So what you're doing here is number 2 in here, and then you do number 2 over here, and then 2. When you have done that, you say there's 2 outputs. I have defined them, the second row of the C and the D matrix were the outputs, and now we can run it and get the state space form. Basically the matrices, when we have the that's what we will get. So when you run it in here, sorry, what did I do? I was on the wrong file. CAMG SYM file is the one that we need. This will work fine if we put numbers. I wanted to show you with symbols. So sorry, we have to make this correction. CAMG SYM is the file that you want, and we're gonna have to define those 2 again. But since we already know, this will only take a moment. So we'll do the same thing. It's just this is the file that works with symbols. The other one works with numbers. So I want to show you the one with symbols first. Otherwise, the easy fix would be just to put numbers, and it will be done. But we don't want to do that. We want to do it right. This would be E sub 6, and then you go over here, and then like that. This would be number 2, and this would be 2, and then 2 like this. So we are ready to run. Let's get this, and then we're running CAMG SYM file in here. It tells you the input vectors, then it tells you what the state variables are, those 3, and then it tells you what the outputs are. See, output 1 is F8, output 2 is E6, and then it gives you the matrices right there in symbolic form. This is the A matrix, then you have the B matrix. Just gonna move it up a little bit like this, and then you hit the C matrix, and then you get the D matrix. And that's how you get the state space form. You have to keep in mind that the derivatives are in this order, like this. See, it's 3 by 3, the A matrix, the 3 by 1, the B, the C, 2 outputs, so it's 2 by 2, 2 by 3 really, because 3 state variables. and then the D matrix is like this. So yeah, that's how you get the automated state space form.